Hello and welcome back to our course on system engineering. We're now continuing in our exploration of supplemental topics and really some advanced topics here. And so hopefully this section will be both motivational and maybe unfortunately a little bit daunting in terms of the possibilities of where you can be going with some of these techniques. So in this chapter, we're going to be talking about graphical modeling techniques. And you might recall that we had these chapters on discrete math and directed graphs. And so we talked about graph theory. So now we're starting to maybe explore that a little bit, but I'm going to nuance that a little bit as we go forward. But having a picture and showing the relationships is a very powerful concept in general. And with Booty and some of their research, they get a lot more sophisticated in that. And so my goal with this chapter is to introduce some of that, but still trying to keep it at a high level. So first, let's talk about this third section in general. So it's talking about 4 additional topics. And so we're going to be talking about methods for data process and behavior modeling. And we'll be considering graphical means for doing that. That's what we'll capture in chapter 13. Chapter 4, we'll be looking at decision analysis. How do we go about making decisions? Chapter 15, we'll talk about system science and analytics. And finally, in chapter 16, we'll be talking about the value of system engineering. I've heard a long time ago, and I've mentioned it before, a manager mentioned that system engineering is like insurance. You buy as much as you can afford, and it actually does save money in a variety of ways. And we have also talked about model-based system engineering as yet another development that is showing merit in a lot of different industries. So this chapter will be addressing the topic of data modeling, process modeling, and behavior modeling. So the focus is on modeling, data, process, and behavior. And we'll go through at a very high level examples of these. And there's many alternative approaches for each of these modeling areas. And so they're introduced. Let me just come back to something from the NASA System Engineering Handbook. And so this is just the general design solution process. So as we're going through the general flow of system engineering, it's nice to be exposed to a couple different types of approaches. And so coming back to how NASA actually looks at these. And so before you can do an analysis, you need to define the alternative design solution. So to come up with some viable candidates, analyze the benefits, pros and cons of each. You want to be selecting the best design alternative. And then from that, you generate the full design description of the selected solution. So you're going deeper on that selected alternative. From there, you want to verify the defined design solution. Does it actually meet everything that you need for what you're trying to accomplish with this mission? Then you can have a baseline design solution specifying the requirements in the design description. And so do we need to use products that are always there, or do we have to develop something on our own? And then there's a logical flow as we go along. And so there's inputs and outputs from this. There's inputs from a logical decomposition and configuration management process, and then there's outputs, the various types of products, requirements documents, and other types of verification planning and logistics. And so that's just a general flow to be thinking about. Well, it's interesting to be considering this word. In some ways, it sounds like you would know exactly what this means, but there's a lot of different sub-definitions of what you can be thinking of models and how that term is applied. So from Booty, there's 3 categories of qualitative modeling used in the development of functional and allocated architectures. There's a data model. So we talk about data models, process models, and behavior models in this chapter. So a data model addresses the relationship among the inputs and the outputs of a system. A process model defines a functional decomposition of the system, the function and the flow of the inputs and outputs for those functions. And finally, a behavior model defines the control, activation, and termination of system functions needed to meet the performance requirements of the system. There's also another area that is included, something called object-oriented engineering, and maybe you've heard of object-oriented programming. And so now we're trying to leverage that in engineering. Is it useful in the software engineering and systems engineering, and uses these three domains. So in this chapter, it's like a how-to or a handbook on quite a number of different modeling approaches. So we have elements here for data modeling, for process modeling, for behavior modeling, and then there's a couple examples for object-oriented modeling. And so we're going to walk through examples of each of these. Most of these, it will pretty much just be a short here, will just be an illustration of a chart, and I won't talk about it in detail. We'll show a comparison between these and the SysML diagrams for the ones that have an overlap. And then we'll have a summary and we'll review some of these things. So first of all, as a reminder, for the SysML modeling language, here are the 9 different diagrams that exist. And there's a logical grouping of really 4 different areas: the behavior, the requirements, the structure diagrams, and the parametric. Parametric is sometimes put up here as another one, as I showed earlier in the class. And so there is a relationship between some of these things going from what we're seeing in this chapter and SysML. And this is just one way of showing that relationship. Data modeling gets into some of the structural diagrams. We can see some relationships there. Process modeling can be viewed to be flowing into the area of behavior diagrams. And then there's a whole more detailed area that's very much in depth talked about in this chapter, behavior modeling. So in general, we can see that there's a connection for a lot of these things. There's also these more software object-oriented type of modeling techniques that there isn't really as much of an overlap with SysML and those. So over here on the far left, there is going to be this flow that we're going to talk about that we showed here in this previous charts. And we'll be just showing an example for each one and quickly go through them. And then I'll review some of the ways these are used in the summary. I'll have a couple of slides that we'll talk about that. So this is an example of an entity relationship diagram. You can see how one thing relates to another: a customer and money, the accounts. You can have sub-accounts. And so here we're talking about the financial industry and how things would flow for banking and money and those types of things. Here is an ERD for system engineering. And we have seen diagrams like this earlier in our course. And so we can be thinking of the overall system, and that the system performs functions, and there's various things that flow in that are important to make functions actually work correctly. And you could easily just go through this in a lot of different ways. You have the functional architecture. You want to be that is then documented into a functional decomposition, and it contains a function. And so just a lot of interesting things that you're trying to graph out the entity relationships that are found. So that's just a discussion for an ERD or entity relationship diagram. For a high graph for system engineering, we have talked about directed graphs or digraphs, and now we're talking here about high graphs. And we see the relationships between various elements. So we have a relationship between the requirements, the functions, the system, and the components. And then we see how there is a temporal component that is also shown here. And there's different types of requirements, and we're showing those input, output, system-wide trade-off, test requirements, originating requirements, and also derived requirements. And so there's traceability. And so there's just some interesting perspectives on how you could be using a high graph. And there was a couple examples when we showed the 4 general categories in SysML and show how one diagram can relate to an entity in another diagram. So we're seeing some connections between what was going on there and what we're showing here in a high graph. There's the data flow diagrams and the semantics that's associated with that. These were 3 equally valid representations of the process. You might want to be thinking and remember that note a process begins with a verb, just as a function or activity due in IDEF0, something that we see a lot with Booty in his development. And so there's different types of nomenclature that are used, the semantics for these diagrams, a double-headed and a single-headed arrow. So we're seeing that. So here are also some other things, branches and data stories and these type of data flow diagrams. And we can start to be taking a logical flow and logic algebra equations and start to have that, see how it would look like with a data flow diagram. So here is yet a more complicated context with external systems that tie in, showing inputs and outputs. And we're seeing that in this more complicated data flow diagram. So that's a couple of examples of the data flow diagrams, and now we have an N2 chart. And so this has come up periodically as we've been doing our flow through system engineering, and we can see how there's a general waterfall progression of what happens here, except passengers. And so this is for our elevator example. Control the elevator cars, move passengers between floors, and enable effective maintenance. And so we've already seen something similar to this, but now we're seeing all of these grouped together as we try and give this tour of various types of graphical approaches for what we can be doing for system engineering. So we talked about data modeling, we talked about process modeling, and now we have a lot more examples for things that would be relevant for behavior modeling. We've had a variety of examples for functional flow block diagrams. And here are just a variety of things that we can be seeing as examples for general behavior diagrams. For finite state machines, or maybe you just want to call them state machine diagrams, which is what SysML calls them. So finite machines are discrete value inputs, outputs, and internal items, and you're showing the relationships between one and another. And in comparison, continuous machines, we have continuous and discrete outputs, inputs, outputs, and internal items. So moving on, for a state transition diagram, you're showing how things flow from one state to another. And so we can have idle, waiting for customer, waiting for access code, and waiting for a customer choice. And so here we're seeing a logical flow in a transactions at an ATM, the logic that has to be designed in that ATM for it to function properly. Going back to our elevator example for a state transition diagram, here we see an example how that would look for state machine representation of that data. And for state charts, here we see an example, an external system state chart for a cruise control system. And so we have the cruise control system, the human that's engaged in that, and the automobile, and all of these 3 things are working collaboratively. If the cruise control is off, then that means a change in state that's going on with the automobile and the way that the human is driving it. If cruise control is on, then they just have to be focusing on the wheel rather than pushing on the accelerator or the brake pedal, perhaps if it's more advanced. Here is a decomposition of the not off state for the cruise control system. So now we're getting a little bit more specific. So it's a flow down, getting more detailed than what we showed on that previous slide. Here is a decomposition of the live state for the indicator of the cruise control system. And so we're seeing a couple more detailed examples of these state charts. Here's a decomposition of the on state for the indicator of the cruise control system. So, and here's the state chart for the entire cruise control system. We put all those things together and in a more complicated fashion, once again, focusing on this cruise control, the on and off, and the what that means for these different more detailed areas. And then finally, we have a Petri net. And so this is something that can get a little bit complicated, but here we see transitions. We see that the functions, relationships that are relating different elements with one another. And so this is just sort of a simple way of giving an introduction to this topic. And we really haven't gone over this in much detail. So I'm just giving you a perspective that this is an existence exposure, that these things are here. And so we can be thinking in terms of sample Petri nets for, say, a concurrent process. So two processes are going on in parallel. And so we're trying to articulate how that would look. Or we could also have a simple communication protocol. And so we've talked a little bit about how we do communication. And here we can be thinking about, do we send a bit of information, and do we wait for an acknowledgement? In this type of protocol, the answer is yes. And so you have to get an acknowledge. And once you get that, then you can continue to move on with what you have for that passing of data. Here is a Petri net with a deadlock. And so this system can be deadlocked if the leftmost tokens are split between resources 1 and 2. So that's just another example of a Petri net. So I kind of went through that fairly quick, and the whole intent, because some of these are quite complicated, is just to give you a survey introduction. And this is just a summary of what is in the text, trying to describe what was covered in this chapter. And I boiled it down to 2 slides. I'll just go over this, and then I'll call it the end for this chapter. So for model-based system engineering, it requires data, process, and behavior modeling. And so those are the main things that we're focusing on in this chapter. So when using multiple approaches to model a single system, balancing or aligning the elements of the multiple models is critical. And so there's several approaches for modeling that we were exposed to for each. So we'll take them one at a time. For data modeling, we got into starting to think about and specify data entities and their relationships. And thus we have this entity relationship diagrams. We provide the basic data modeling capability that are probably the most widely used in the data modeling techniques. Attributes of each data entity can be developed, and HiGraphs extends the data modeling by adding subsets, representations, and cross-product relationships. And the work that we do with SysML, with some of the modeling in the class, I think you'll get a chance to see that. And then for process modeling, they focus on 3 things. So these capture the relationships among the functions in the decomposition of the inputs into outputs. So for IDEF0, one of the things that the author Booty often goes to, they represent execution resources representing the portions of the system's allocated architecture, control trigger function activation, and policy instructions for function implementation. We have seen a lot of examples throughout the course for data flow diagrams that contain a data store that is useful to define which data elements are contained in a database. They are widely used but are least standardized of all the modeling techniques just discussed per se. And then there's these N2 charts. These are the simplest but least graphical representation of a process model. So that's the data modeling and the process modeling. And then we have the behavior modeling. And so behavior diagrams add functional flow block control structure to represent serial, concurrent, repetitive, replicated process execution, and rule-based selection of functional outputs. And we were exposed to a variety of types, the functional flow block diagrams. And so we will be exploring block definition diagrams in SysML. We have logical flow diagrams, and this adds the idea of transition to data flow diagrams, which suggests that the system modes and functions are identical. We talked about finite state machines or state machines, state transition diagrams, state charts. These are a generalization of the state transition diagrams that provide a semantic and syntax for modeling complex systems. And finally, Petri nets, they add mathematical models defining what can be done and offer analytical results without having to just see that through the result of simulation. Okay, well, that's going to conclude our chapter, and we'll call it an end for now. Thank you.